Section 3.2 is called differentiability. Quite a big word, but we're going to be talking about how the derivative might fail to exist. So let's take a look at some of these graphs here. This is called a corner. At a corner, one cannot just draw one tangent, but we could actually draw a whole bunch of lines that only hit at one point on that curve. So f prime of x does not exist there because the tangent line slope doesn't exist there. Okay, so if there's a corner, there's a problem. This is called a cusp, where you have like a seagull, and here's the dot there. Again, does not exist. What about right here? Let's zoom in on this third guy. Right in this middle, what happens right there with this roller coaster? If you were traveling along this roller coaster, what would you say about yourself right there? You might say you are straight up and down. Well, you guys remember? A horizontal line would be slope equals 0. What is a vertical line? Well, a slope is undefined. Well, if the slope is undefined, then so is the derivative. Does not exist there at a vertical tangent. Vertical tangents cause the derivative to fail to exist. And then, of course, this one's pretty obvious. Right here we have a jump, so there's no way to draw a tangent there. So again, the derivative doesn't exist. Differentiability. What that means is if a function has a derivative everywhere, if a function has a derivative everywhere, we say it's differentiable. Differentiability implies there's local linearity there. Now that's quite a mouthful, but basically if you draw a curve and you say, hey, f prime exists there, yay. Well, you know what, we could zoom in and say, well, if f prime exists there, then we could think of it as being a little line segment there. A little line segment. It's called local linearity. Local linearity. So if the derivative exists there, there must be a tangent, which means there must be a really tiny little line segment we could think about there at least, and that might be helpful to use that. So let's read what this says. The summary here is if you zoom in enough to a function that has a derivative there at x equals a, the function will resemble the tangent really close to a. When I zoomed in there, you remember how the tangent line that I drew was on top of the little line segment. They're basically the same thing when you zoom in. This is more of a concept to think about, which is why I say, hey, chew on this. All right, let's move on. All right, you can find slopes of tangent lines on your TI-83. How exciting is that? This is called doing a numeric derivative, because you don't actually, your calculator doesn't give you the machine, you know, the f prime of x. What it does is it spits out the slope of the tangent line wherever you tell it you want the information. Wherever you tell it you want the information. So at this point, you're going to need to have your TI-83 plus out, and we're going to look at the actual keystrokes, what you need to type in to do this. And this is a required thing for the AP exam, and we're going to use it a lot this year at times when, you know, finding an f prime of x is just impossible. And so you just use your calculator to find f prime of a, where a is some number, and you get that specific slope that the problem was asking you about. So here are the keystrokes on your TI-83. Suppose that they ask us to find the slope of the tangent line on this x cubed function at 2.75. So we only need one slope value, so maybe using the calculator is a good idea here. Here's what you're going to do. You're going to hit the math button, and that gets you into that those different tabs. You're going to scroll straight down to where you see n deriv, and what that means is numerical derivative. You want to find a number, and it's going to be a derivative. So numerical derivative. Then you're going to type x raised to the third power, and then you're going to type a comma. Now the reason we do that is because we have to give a little extra information to the n deriv function. It's called a computer function. It's going to calculate the derivative. So we give it the function, we put a comma, and then we tell it what the independent variable is. And here the independent variable is x. So we put x, comma, and then the last thing we have to put is our a value. It's where we want to know the derivative. We want to know the derivative at 2.75. Hit enter and you should get the answer. 22.6875. So please take time right now to make sure that you can put that in the calculator and that you get your calculator to spit out 22.6875. As I said, what you just did was the numerical derivative, and it was abbreviated on your calculator nderiv. And what is the meaning of this answer after we find that number? On the last page we found the number 22.687501 actually. That is the slope of the tangent line at x equals 2.75 on x to the third, on the function x to the third. That's the meaning of it graphically speaking. It's the slope of the tangent line, but it's only the slope of the tangent line at x equals 2.75. Theorem 1 says differentiability implies continuity. So if f of x is differentiable, that means the derivative exists everywhere on its domain. If a function is differentiable, it means the derivative exists everywhere on its domain, so no corners and cusps. So if it's differentiable everywhere, then f of x is continuous. All right, so if they tell you it's differentiable on its domain, then you also know it's continuous everywhere because, after all, if there was a discontinuity, that would be a hiccup in the graph and the derivative wouldn't exist there. So it must be continuous. The function must be continuous if the function is said to be differentiable. Now what about the converse? If I said, hey, can you draw a continuous, so if f of x is continuous, is it also differentiable? Does continuity imply a differentiable function? I'm pausing a bit so you can think about that. Is f of x, if f of x is continuous, does that mean it's differentiable? Not necessarily differentiable function. And the reason is because look at this. I'm going to draw a check mark. That what I just drew is continuous, but look at that. There's no f prime does not exist there because it's a corner. F prime does not exist at corners and cusps. So therefore I was able to draw a continuous function that has a derivative that does not exist at a spot. Okay, so it's only differentiability implies continuity, but not the other way around. All right, the intermediate value theorem for derivatives. We talked about the intermediate value theorem, and it had to do with, if you recall, if you're traveling down the road, and at some point you're at mile marker 1, and then later on you're at mile marker 10, you must have gone through all the mile markers between 1 and 10 at some point in between. Okay, at some time in between. Well, you know what? The same thing holds for derivatives. Okay, at point A, we might have a slope of, let's say this slope is, let's say 6. And then at point B, let's just pretend that this is slope 10. All right. Now, what the intermediate value theorem says is that between A and B, if you have a continuous differentiable function, you will have to hit all the slope numbers between 6 and 10 at some point in between. In order to go from 6 to 10, you must be at a slope of 7 at some point. Looks like it's maybe up here. A slope of 8, a slope of 9, a slope of 10. You got to hit all the numbers between 6 and 10. Now notice it actually goes horizontal here for a moment, so it actually, the slopes dip down for a little while, down to maybe 0, and then they go all the way up to 10. But all the intermediate value theorem says is that there are, for all the values between a and b, there exists a point in between where all the values between 6 and 10 are hit. It takes on all the values between f prime of a, that's this guy 6, and f prime of b, 10. All the values between 6 and 10 are taken on somewhere. So in my example, we could talk about, maybe I'm going, because remember slopes of tangent lines are actually rates of change at an instant. So we could say at this instant I'm going 6 miles an hour. And then at this time, at this instant, I'm going 10 miles an hour. So wouldn't you say that I must have an instantaneous rate of change of 9 at some point, and of 8 at some point, and 7 at some point? So that's another way to think about this intermediate value from theorem of derivatives. All right, let's give this, this is kind of a review question in a way. We're going to find f prime of 10 right here. Now rather than using our good old-fashioned definition of derivative and doing all that f of a minus f of x stuff, because we would have to multiply out this trinomial, and goodness gracious, who really wants to do that? So why not use our calculator at this point? You would type the numerical derivative, and by the way, why don't you pause the video and give it a try all on your own and see if you can remember what you type in. Numerical derivative of, now you need to open a parenthesis, x minus 7 raised to the third power, and then plus 1, and order of operations will take care of itself. It'll add the 1 after doing the cubic. All right, then you should have put a comma. Then you got to tell it what the variable is. In this problem, it looks like it's an x, so I put x, comma, and then you need to put that 10 value here at the end, comma 10. Hit enter, and what do you get? All of our calculators should spit out the same thing. It's 27.0000001. Now, I'd like to now talk about what's going on here. Why is it seems almost like error. Like the slope of the tangent line is probably exactly 27, so why is the calculator doing that? And this is a question on the homework. The calculator doesn't know calculus. Let me repeat that. The calculator doesn't know calculus. It's actually not using calculus. What it's doing is it's creating two data points on this function. It's finding f of, and I'm just going to sort of make this up, but it's going to find f of 10.00001, okay, and get a number. And then it's going to go the other way, 9.9999999, and it's going to get another output. All right, so it's like a tiny secant line is what it's creating, and it's going to find the slope of that tiny secant line. So that's how your calculator finds the slope of the tangent. It actually creates a really small secant line to do the simple calculation, rather than actually finding the derivative and then plugging 10 in. All right, I think that wraps up this section. Good luck on your homework. Get right to it and bring in some questions. The good news is that in 3.3 you're going to learn a shortcut for the derivative, and then it gets really fun. All right. Good luck.